I'll just I'll just keep the video turned off for the moment, if that's okay.
Yeah, yeah.
Uh, because connectivity issue is like always a problem.
Yeah,
Okay.
we were not getting any video. We were,
Oh, my video was turned on so far, so
oh, okay.
anyway.
Maybe it is in some other place or something. Okay, anyway, you can turn it off if you wish. Yeah.
Okay. Okay. Thank you. Okay. Good afternoon,
It's always
everybody.
been like that. It's always been like that. Yeah, we have always been seeing this. Ah, that was long back. Yeah. Okay. Okay, so we are happy to have Lopamudra Mukherjee from the University of Kolkata, and she'll be telling us about flavor physics as a window to BSM scenarios. Lopamudra, please carry on.
Thank you. So good afternoon, everybody. I will today speak about flavor physics as a window to beyond standard model scenarios. And before I go into the talk, okay, why is the slides not changing? Do you see my slide? Okay, now there. Yeah, before I go into the talk, I would just give a brief introduction about myself. So I completed my bachelor's in physics from Jogomaya Devi College, University of Calcutta in 2014, followed by a master's from Presidency University in 2016. Thereafter, I joined the doctoral program at IIT Guwahati under the supervision of Dr. Soumitra Nandi, and submitted my thesis in 2021, defended in 2022. And I have had several postdoctoral experiences, first at the University of Mississippi for a year, and then I was a visitor for a brief period back at IIT Guwahati. And then I spent 2 years at Nanka University. And since May of this year, I'm a research associate at the University of Calcutta. My primary research interests are flavor physics phenomenology, beyond standard model of particle physics, model building, colliders, dark sectors, etc. And other than research, I've had a little bit of teaching experience during my PhD tenure at IIT Guwahati, during which I've conducted lab courses for B.Tech and Masters, as well as tutorials for theory courses. All right, so as the title suggests, I'm going to speak about flavor physics, particularly focusing on quark flavor physics. So what is it all about? We know that there are 6 different flavors of quarks in the standard model, 3 up type and 3 down type. And the weak interaction mediates transitions between the up and down type of quarks. Similar flavor transitions or flavor mixing is also observed in the leptonic sector, but okay, I'm not going to focus on that today. So this quark flavor mixing is characterized by a 3x3 unitary matrix, which is known as the Cabibbo-Kobayashi-Maskawa matrix. And all parameters of this matrix, so you can parameterize this matrix using 4 independent variables. And all of these parameters are free, which need to be fixed from data. So you need to, and by data, I mean flavor data. So since all quarks hadronize because of the strong interaction, you don't see quark level transitions. And they are only studied through decays and mixings of mesons and baryons, which are the bound states. So why is it important? There are many reasons why quark flavor physics play an important role in our understanding of the standard model and beyond standard model. So firstly, as I said, it tests the standard model. As I mentioned, the CKM elements are like free parameters. So, and they need to be determined from experimental data. Hence, for precision studies, probing CP violation, testing the CKM unitarity, quark flavor physics play a very important role. So this is the unitarity triangle, as you can see in the rho bar eta bar plane. And this blob here was the constraint on rho bar eta bar from all possible, measurements, mixings, everything, semileptonic, leptonic decays, whatever, provided by the CKM-FITTER group in 2012. And in a period of about 10 years, you can see the level of precision that has been reached, such that this little blob here has almost become a point, a tip in the plane. So quark Flavor physics, I mean, the data, we have plenty of data, and with more and more data, our understanding of the standard model is also getting better. So we are reaching the high precision era. Next, quark Flavor physics is also important in the understanding of QCD. So as I mentioned, you don't observe free quark transitions. And so when you have to deal with mesonic or hadronic transitions, principles of perturbative QCD fails, and the ignorance about the non-perturbative contributions are dumped into objects which we call form factors. And these form factors are then extracted from experimental data. More importantly, flavor physics serve as a very powerful indirect probe of new physics. We all know that, in spite of being a very elegant and predictive theory of nature, the standard model cannot explain all observations, which then demand the presence of new physics. Now, the new physics scale can be both heavy or light, and flavor physics is able to constrain both. But let's suppose the new physics is heavy and beyond the reach of the detector. This is a beautiful presentation of indirect searches and colliders. So let's say you have an event distribution given by these data points, and your standard model expectation is given by the blue line. Now, if the new physics is very heavy, as I said, beyond the reach kinematic limit of the detector, you will obviously not see this peak here. But what you may probe is this tiny deviation in the measurement. So, and these are especially, done in flavor physics. The rare decays especially are crucial, and such deviations are observed. For example, if you have, a B2SLL kind of a transition, which in the standard model is suppressed because they occur at the one loop level, but, heavy new particles like leptoquarks or heavy gauge bosons, Z primes, they can induce such transitions. And therefore, you will observe tiny deviations in the branching fractions or, observables related to this decay. And therefore, such deviations give us hint of heavy new physics, one which is beyond the direct reach of colliders. Signs of lepton flavor universality violations could be there, as opposed to what we expect in the standard model. And that also indicate the presence of some, new physics. As I mentioned, flavor physics can also probe light feebly interacting new particles, which in that case you look for missing energy events, displaced vortices, or little resonances, bumps in rare meson decays. So because of such wide range of motivations, a huge effort is put experimentally to measure the flavor observables. And in this game, the key players are LHCb at CERN and Bell2 at KK. Both are involved in precision measurements, while Bell2 also have a very advanced program for new physics searches, especially in B and tau lepton transitions. Then there are some small scale but targeted experiments like NA62 at CERN and COTO at JPAR, which study the rare kaon decays. Then we have these general purpose experiments like the ATLAS and CMS, which, other than their, they are basically the discovery machines, but then they also study CP and lepton flavor universality violations, properties of beam mesons, and so on. And then we have some proposed future colliders like the FCCE and CPC, which aim to study flavor changing processes beyond the reach of LHCb and PEL2. Hence, we have a large data set to work with, plenty of observables, and therefore its flavor physics is like the hub for new physics searches, and it's like the ideal time to work in this area. Now, when I talk of flavor transitions, they are basically of two types in the standard model. One is the flavor changing charge current transitions, shown here, which occur at the tree level and are directly proportional to the CKM elements. Therefore, they are used to extract standard model parameters like the mixing strengths or even probe CP violation, but they may also be useful in probing new physics. And then there are the flavor changing neutral current transitions, the FCNCs. I already showed you an example of B2S transition. They occur only at the loop level. So they're loop suppressed, they're Cabibbo suppressed, and therefore they're extremely sensitive probes of new physics. So throughout my research career, I've worked both on these charged currents and neutral current decays. And in the charged current sector, I have several publications, as you see here, often having implications in other sectors like dark sectors or neutral current decays, electroweak precision observables. Many of these studies are also done using effective theories. So we put constraints on model independent new physics in that case. So I will not be able to talk about all of these works within the time frame, but I will highlight a few significant ones. So one of my significant contribution has been in the extraction of CKM parameters from a global fit to data. Now, usually such sophisticated analysis is performed by the CKM fitter group. They do it year after year and present their results and constraint on in the unitarity constraints on the unitarity triangle, as I already showed you a few slides back. But in 2021, we independently performed a similar analysis by utilizing updated measurements on inclusive and exclusive semileptonic charge current decays, as well as available data on leptonic and non-leptonic decays to put constraints on the CKM Wolfenstein parameters A lambda, rho bar, and eta bar. And this was before CKM fitter group presented their results. So here I show you a comparison of our 2021 fit results compared to the CKM fitter group results. And as you can see, our results are consistent with each other within the 1 sigma errors. So this was a significant achievement in this direction. Now, because the CKM matrix and the data is now very precisely known, we not only perform.
Sorry, can I ask one question in the previous slide?
Yes, sure.
So the data that you use for this is all of the flavor data that we have, or some subset of it, or
No,
what
all
does
of
CKM
it.
fitter do, and what did you do differently, or is it pretty much the same?
Okay. So in that case, I will just go to the backup where I have actually the entire list present. So this is the entire list of observables that the CKM fitter group uses. So there are leptonic decays, semileptonic decays, mixing, constraints from mixing, some data from nuclear decays and so on. And we actually consider all of this. Okay. The one difference that between their analysis and ours was when we dealt with the angles, alpha, beta, gamma, these angles here. And that is because each of these, when the CKM fitter do their analysis, they extract these angles separately from, the hadronic measurement. So For example, the alpha is measured from the time-dependent CP asymmetry in B2 pi pi. And that itself is like a very involved analysis. Each of these, alpha, beta, gamma, all of those, okay? So what we did is we did not perform that analysis ourselves, and because we saw that there was no new update in this sector since the last CKM fitter result. So we just took the values given by the CKM fitter group in the previous year and utilize those numbers to fit a lambda rho bar eta bar. Other measurements, there were some, in semileptonic and leptonic decays, there were new updates, which we included in our analysis. Also for VCB especially, there was new data from the Fermilab lattice collaboration on the form factors. So we actually performed the B2D star LNU fit ourselves to extract VCB. So there's VCB from B2D and B2D star, and as you see, so we first update, VCB using the new data, and then use this as an input when we do the CKM fitter, the CKM fit. So this
Sorry,
was
sorry.
qualitatively, yes.
If you take the alpha beta gamma that from CKM fitter,
Mm-hmm.
that is three significant inputs, and then it is not so surprising that you will agree with CKM fitter, right? Because you have taken three numbers from them.
Right. So as I mentioned, there was, no new data on, let's say, the B2 pi pi, B2 rho rho that affects alpha, or B2 decay, BS to DSK decays which affect gamma, and so on.
Okay.
So there was no new update since the last CKM fitter, when we did the analysis and compared to the previous year, let's say.
Okay. Now, why is there a fourth angle, this five star or something there? There should be three
Uh,
angles, no?
There are three angles, alpha, beta, gamma. Phi s is
Oh, that's
basically
phi
the
s. Okay, all
strong
right. Sorry. Okay.
ferrets. Yeah.
Yeah, yeah. Okay, got it. Yeah. All right. Sorry, you should continue. Yeah.
So there were obviously qualitative differences between the analysis that we did, but thing here is they are like a big group doing this, they have sophisticated techniques to handle all kinds of data. We didn't, so it was, you might say, a simplified version of the CKM fitter analysis, but our results match, to a pretty good extent, as you can see here.
Okay.
Uh, yes. So then moving on, as I mentioned, so what we did is we not only performed the global CKM fit to data in the standard model, we also utilized these precise CKM data to put constraints on a benchmark new physics model, which again, nobody had attempted before. So we considered this simplified dark matter model with a spin zero mediator S that couples to the quarks in this fashion. So we have a scalar and pseudoscalar coupling. And in order to avoid significant flavor violations, we rescale these couplings with the standard model Yukawa couplings Y, as you see here. And in presence of this Lagrangian, you'll have contributions to flavor changing charge currents transitions, like a D to U transition via vertex corrections. So you'll have, this kind of a vertex correction here, which will be affected by the new couplings. So we parameterize the D to U transitions using this effective Hamiltonian, where OV1 and OV2 are the left-handed vector and right-handed vector operators, and these are the corresponding Wilson coefficients, which depend on, of course, the new couplings, GS and GP, as well as the cutoff scale lambda. Now, all these leptonic, semileptonic decays would be modified and the modification will be in the vertex. But if you have a purely leptonic or a pseudoscalar to pseudoscalar transition, then the modification will be of this form, where you can actually factor out the new contribution as an overall correction factor in the CKM element. But if you have a pseudoscalar to vector meson transition, or you have a vector meson in the final state, then in presence of this right-handed current, the decay distribution itself will also be modified. So proper care should be taken so that you don't disturb the decay distribution. So I will show you how this modification arrives, comes. So these are the different
Sorry,
decay
one
rates.
question.
Yes.
It doesn't couple to the strange quark or what? This
It
this
does. This
S.
is, generic Lagrangian. So you will have all the kinds of quarks. GS and
Okay.
GP are just the scalar coupling and the pseudoscalar coupling.
So they couple to all of the quarks, huh?
All quarks, all possible quarks. So,
And
pi.
then you maybe will show, but all the constraints you will apply from all of the flavor channels and
Yes,
so on.
yes, all,
Okay.
exactly. Whatever
Okay.
was
One
used.
other question. What is DM here?
Where?
It says SDM model.
Simplified dark matter model.
Which is the dark matter here? S is not
So
dark matter,
I'm
right?
not, S is not dark matter. I've not,
But there
I'm
is
not,
some other dark matter.
some other fermionic, dark matter could be there, that
Okay.
couples. Yeah. So
But
S then becomes a mediator.
you won't have
But
any
that's like
connection to the
not,
dark matter.
no, I mean, not directly, won't have a
Okay. All right.
connection
Okay.
to,
Okay.
I mean, from the CKM side, you will not have a connection to that. So that's why I don't write it, but I can talk about it if you want. Okay. So yes, I was showing the decay distributions for purely leptonic, pseudoscalar to pseudoscalar, and pseudoscalar to vector meson transition. And you see here, for these two, you will have these overall factors, correction factors. But in case of a pseudoscalar to vector, the new physics is all entangled in the decay distribution. You cannot factor them out. So you actually have to consider data on the decay distribution if possible. I mean, you don't you want to mess up the decay distribution if you have such corrections there. So yeah. So that was one tricky thing to actually consider, take into account. So with that, and considering all bounds from CKM, and we also have top. So there were collider bounds on T2BWDK. So considering all of that, we constrain this effective coupling CT, which is a combination of GS and GP. You'll see, all corrections okay, what happened? Do you see my slide changing?
See slide 14 right now.
Yes, I know. And I'm trying to go back to show you what city was, but okay. I'm not able to go back or even go forward in that.
Hmm?
Let me. What happened?
So if you click on the slide and then maybe try to go back.
Yes, I'm trying that, but it's not changing. I don't know what.
Is it?
Okay,
Now
okay,
it's
okay, okay,
changing.
okay. Now.
Yeah.
Okay, now I went way too. Okay, I think some delay.
Is that on your computer or what? The delay must be on your computer, right?
Yes, it's on my computer. Yeah.
Okay. All right.
Uh,
Now we
Because
see 15.
now I see
Huh?
15. Okay, now, yeah, okay, better.
Ah,
So CT is, as you can see,
cheese.
it's a combination. So we are not able to constrain the GS and GP separately. We always get it as a combination. The constraint is on the combination. So this is the constraint that, of course, for varying cutoff scales, the constraints become tighter. And yeah, so with increasing cutoff scales, the constraint on the coupling basically becomes tighter. This is, I think, a similar thing, but so this is maximum allowed GP in absence of a GS coupling, let's say.
Sorry, I'm confused. So shouldn't
So
it
this is
be
the
the other
constraint.
way?
Sorry.
No, for a higher lambda, shouldn't your constraints weaken on coupling?
No, because you have the logarithmic contribution on the Wilson coefficient, so your couplings basically increase with increasing lambda
So
logarithmically.
this is not decoupling then.
Decoupling as in?
No, as I take lambda larger and larger, your contributions keep growing. That's non-decoupling, right?
Yes, yes.
No, that would be extremely problematic as a field theory, no? Then I'm sensitive to arbitrarily high lambda.
But yeah, I mean,
Unless there
how
is
can I
some
put it?
non-trivial
Unless,
relationship between coupling and lambda. The coupling must, reduce with lambda. Otherwise, you have a non-decoupling behavior, right?
yes, so you have this coupling varying as 1 over Wave square. So the coupling reduces with, okay, okay, not directly with lambda, but these couplings, the Wilson coefficients, they increase with lambda, but how do I put it? But then they increase logarithmically because the contribution that comes here is from the loop which is divergent.
No,
So
then
you
you
all
don't
have,
have, Jim suppression or what? I mean,
mm,
this would be extremely troubling if this is in fact true.
no, no. So you have all these Vij's here, no? So you'll constrain them automatically. Uh,
You have absorbed your ultraviolet factors into your couplings. That cannot be because then you have a runaway theory, right?
Sorry, I cannot hear you.
Oh,
Sorry. Can you hear me now?
Yes, yes, yes.
Yeah. So you've absorbed your ultraviolet factors into your couplings. So you are
Yes.
going to have a runaway theory because you are not dealing with those divergences at all, no? They should be at some point, if you have a renormalizable theory, they'll go away, right? But once
Yes.
you
Yes.
put it in the coupling constant, it's there forever. So uh, why did you want to put the log factors in the coupling constant?
no, that's
Mm,
just the result of a calculation, right? You compute the loops and you will
yeah,
get what.
compute
But here
the
you have an effective field theory, right? That effective field theory cannot have, unless you say that it's not valid beyond a certain scale, right?
yeah. So it will not be, of course, valid beyond this.
So what
You
is
can't
lambda
take.
here? What should I, in your calculation, what is lambda?
So I think we just considered 1 to 10 TV, not more than that.
No, no, no,
No, no.
but
How does it exist your
MS
calculation?
should be appearing somewhere, right?
Uh,
And presumably lambda would be related to MS because that would be your new physics scale.
MS as in the strange
No,
quark.
does lambda appear in your propagators? Or in your integral phase space integration? Where does it appear is the question, right?
It appears when you calculate this loop, and in the
No, if you
divergent part
calculate that
of the
loop,
loop.
that loop
Yeah.
knows only about MS as a scale. It doesn't know about anything else,
No, she's
right?
probably
Oh, okay.
integrating it from
So
Okay, okay.
lambda.
you must be calling
Yes,
lambda
yes.
MS as lambda, right?
MS. Okay, okay. Yeah, correct, correct. So, yeah, you'll have so the MS contribution. So we have so when you need to do the renormalization, this cutoff scale appears, right? And the MS dependent part is
No,
actually
it's. Are you doing what kind of regularization are you doing?
a cutoff
Ah,
regularization, right?
So this
And
lambda is actually the upper
the
limit
cutoff scale,
on the
upper limit
integration
of,
variable, right?
yes, yes.
Yeah. So this is like Polyvillar's kind of thing. I don't think this
Yes.
has anything to do
no,
with
not
MS.
polyvelars, but
No, it
momentum
does
cutoff.
not have
Momentum
anything to
cutoff.
do with MS. It does not have
No,
anything to do with it.
independent of what, if you don't care about gauge invariance,
Hmm.
then momentum cutoff is okay.
Yeah.
But independent of what regularization you use, if you see a non-decoupling behavior,
Hmm.
I believe you have to be worried
Yeah. Yeah.
because now you're sensitive to arbitrarily high lambda scale. The only way to save this thing is if GS and GP, you make it dependent on lambda, but there is no way you can make it because that's like fixed numbers.
Yeah, and but that is what you constrain from the data,
No, it's not a question of what you constrain from data, but if I take lambda higher and higher, your contribution grows, right?
a
Which is
contribution
why
grows,
we saw that very puzzling
yes,
plot. If you take a larger lambda, you have a tighter constraint, and that's
yes,
not usually seen in any theory.
See, you think
Because
of
as
it
you take
physically.
lambda bigger, you will decouple away the new physics,
Correct.
and
Absolutely.
you must have a decoupling behavior if you have a sensible effective theory. Otherwise, you have a problematic effective theory.
Mm,
But anyway, this is for you to maybe consider and
Yeah, because
perhaps.
think of another example. No, if you couple this to gravity, for example, which is so weak, but then the lambda is so high that that's going to give you huge contribution, right?
right.
So there is something that in your cutoff, your log scale, something has to be absorbed in the coefficient and should not be left as log lambda. Okay, you kind of think about that a little bit.
Okay, sure.
Okay,
Okay, you
continue.
should continue.
Thank you. All right. So another set of very interesting observables in the charge current sector have been the lepton flavor universality ratios in B to D and D star L nu decays, which we call the RDR D star ratio, which is the ratio between the branching fraction of B going to D or D star tau nu with respect to B going to D star L nu, where L are the light electrons. Now, since standard model is lepton flavor universal, any deviation from universality is a smoking gun signal of new physics. And these measurements are relatively clean, both theoretically and experimentally, because some of the major uncertainties coming from the hadronic form factors or experimental efficiencies cancel out in the ratios. So, making them, clean tests of new physics. So here is a summary of all measurements as of spring 2025. And this here is the standard model, while the world average lies here, which is about 3.8 sigma away from the standard model expectation. And this has been a long-standing tension, and several authors have tried to explain this from using various kinds of new physics approaches. However, what is more interesting are the angular observables, especially in the B to D star L nu mode. So if you consider the full four-dimensional decay distribution, then you have four kinematic variables. So the Q squared, which is the lepton neutrino invariant mass squared, and three angles, theta L, theta D star, and chi. And new physics operators actually influence these angles in different ways. And so the asymmetry observables are extremely sensitive to new physics, and they also reveal more information about the new physics Lorentz structures compared to the LFU ratios. So, for example, if you consider, let's say, the forward-backward asymmetry, which is the asymmetry in the number of fermions produced in the forward region of the detector versus the backward region, and plot it as a function of Q square, then this is what you observe. So the black curve here is a standard model, which is plotted using the CLN form factor parametrization. And the orange, red, and blue curves, they are all new physics curves. I mean, they have a certain new physics put in them. What new physics is not important, but they have the same new physics, but they're plotted using three different form factor parametrizations. And as you can see, they're all, overlapped, and it's very difficult to disentangle the new physics from the standard model due to the heavy dependence on form factors. So what we do is we consider delta angular observables, which are potentially more sensitive to new physics. So these are the delta observables. Yes.
What is this that shaded band there?
That's the error on the coming from the errors on the form factors. So
Like that, like kind of light beige kind of thing that
yes, so it's corresponding to the orange curve. So that's the orange and with the
I
thick
see.
band there. Depending on the form factors, the errors are either small or large,
Sorry,
with
where is the new physics here?
So the black curve represents the standard model curve,
Ah,
and the
okay.
other three are the new physics curves. I mean,
Okay.
a certain new physics, but we what is important here is that different. If you are using different form factors, then the errors are different, and so it's quite entangled, and you're not able to separate out, or you cannot reliably extract new physics from such measurements,
Okay.
uh, is what I wanted to say.
And the new physics is this is showing about the maximum possible deviation from the standard model or what?
No, the new physics, what we considered, okay, I have the numbers, but let's say, okay, some values of GL, GR, and GP, vector or a right-handed pseudoscalar coupling, some values. I think this one corresponds to this particular one of these cases.
Sorry, we are not talking about the same scalar theory, but different theory
No,
now or
no,
what?
it's a different theory
Okay.
that we are considering now.
Which you
Yeah.
have not, like said what it is, right? I mean, it's some
No, I've
theory.
not said. Yeah.
Okay, all right.
The point here was, the theory is not important, but
Okay,
we need to first disentangle the dependence on the form factors. I mean, reduce the
okay,
dependence on the form factors when we are dealing with angular observables.
yeah. And what is the forward direction here? Like this is with respect to what? This is B to D star L nu, is it what you're talking
So
about?
yeah, B to D star L nu. So uh, so if this is the Z direction, then in this plane, so let's say the B-decays, and in the lepton neutrino invariant mass plane, so you'll have, so theta L is okay. How do I? It's the angle between the direction of the lepton and the direction opposite to the D star. So you'll have, okay. How do I say?
The forward and backward is with respect to theta L or something else?
Theta. So it's with respect to the theta L direction. Okay.
I see.
Yeah. That's what I wanted
Okay.
to say. In this
All right.
plane,
Okay.
basically. Yeah.
Okay. All right.
Okay. So we considered these delta angular observables where we consider differences in a particular observable in the muon mode with respect to the electron mode. And when one considers new physics, we consider new physics only in the muon mode and not in the electron mode. So the electron mode basically explains the standard model. So, and when we plot the delta observable, let's
Sorry to
say,
interrupt, but sorry,
yes,
that means that the new physics will differentiate between muon and electron.
muon and electron, yes. So it has to be a lepton specific new physics, let's say.
But then would it be okay from mu to E gamma constraints and so on?
Yes.
Have you checked that?
Because mu to E gamma, uh, this is, you'll have, particularly in B2 D star L nu decays, what we need to check is the B2 D star E nu and mu nu branching fractions are very precisely known. So the new physics would basically affect the overall branching fraction. So mu to E gamma, I don't think would be affected because we are not considering a specific, uh, a new
Yeah, no,
physics
I
that would
understand
allow
what
this
you're
kind of
saying,
a
but no, I
transition. Yeah.
understand. I understand what you're saying, but I guess my point is, if you go one level deeper and look at a specific example which will give you such physics, then
Yeah,
that
then
same
you need to
physics may
check
also.
that kind of a constraint, but here we are like working with an effective theory. So this one.
Yeah, but it should have some realization in terms of some UV completion, right? And if there is
Uh,
no realization, then this is pointless, right? I mean, you have to have some physics which will give you this effective theory. And that was the only point. I mean, if you generically look at these kinds of physics and ask what is mu 2 e gamma, unless you
So
have some reason why this should.
once you derive, constraints on these model independent new physics, then, when you go a level deeper, you already know that, this constraint is there. If you have, you'll obviously consider other possible constraints that would appear, for example, mu to e gamma, because, here we do not have let's say a new particle or that would allow such kind of a transition, let's say.
Yeah, my only point is if you look at constraints from mu to e gamma,
Mm-hmm.
and if it happens that that physics demands that there be no difference between muon and electron couplings,
Mm-hmm.
then you don't have the freedom to pick what you're picking, is all I'm saying. That's my only point.
Also in B-decays, is that?
Anywhere, I mean, mu to e gamma might generically, usually it constrains it to be a Flavour universal coupling. If you introduce Flavour changing there, mu to e gamma would get induced by any new physics. And because that
Because,
constraint is very
with
tight.
respect to, other Flavour observables, I can tell you, if you consider, let's say, B to K, L plus L minus, where L is either an electron or muon. And if you look at the current experimental data, then the branching fractions in the muon mode um, actually are have some deviations with respect to the standard model, while the electron mode actually respects the standard model. It's well measured. So there are hints of
So
new
you're
physics
thinking
in the
about RK,
muon mode.
RK star, right?
No, so RK star is not there anymore.
No,
But if you
which
look at
which other
individual.
observable are you thinking of, which would differentiate muon and
Oh,
electron?
so there is this angular observable P5 prime in B2K star mu mu, which is deviated. Then you have BS to 5 mu mu branching fraction, which is,
But they have not shown non-universality, right?
sorry?
They don't show non-universality between electron and muon couplings.
What I mean is in the standard model, B to K, E plus E minus and B to K mu plus mu minus have the same branching fractions, right? Which is why when you take the
Yes,
ratio, they cancel out and you get one.
right.
Uh, but even though at present, our the ratio is one, or the
Yeah.
anomaly there is not there, the individual branching fractions for the muon and electron mode are not consistent with the standard model expectations.
And with
Okay, so there are
with
these
what significance?
about 2 to 3 sigma.
Okay.
Okay, so
Now,
it's not very strong,
are you
but
going to be changing muon and electron coupling here at that level, a small level? Then it's fine. But if you make a big difference here, then I would worry about other mu to e gamma kind of
no,
effects.
no, that is what I'm saying. You cannot, the couplings cannot be arbitrarily large. So you have to, because here I'm talking about the angular observables, but the respective branching fractions of
Hmm.
B2D star mu nu and B2D star E nu are known to quite, I mean, they are known very precisely. So
Right.
if you are considering new physics, then you have to respect I mean, the branching fraction measurements have to be respected. So the
Okay.
new physics cannot be I mean, way too large, but
Okay.
there are possibilities of having, tiny new physics, present in let's say the muon and not in the electron.
Okay.
But the point is, how do you extract that tiny new physics there? If it's
All
not
right.
in the, you don't see it in the branching fraction, but there is a way to actually observe it in the angular observables.
Okay. All right. Yeah. Sorry, you
Yeah.
should continue. Yeah.
Yeah. So yeah. So, as I was saying, the new physics is considered only in the muon mode and not in the electron mode. And then we plot this delta AFB as a function of Q squared. Again, the black here is the standard model, where we find an almost exact cancellation of the hadronic uncertainties. And these, again, the red, orange, and blue curves are the new physics curves. Okay, same new physics that we considered here. It's the same kind of, let's say, new physics. And for different form factor parameterizations, as you see here, but the dependency or the uncertainties are reduced to a greater extent such that you can reliably extract the new physics uh, with respect to the standard model. So now, as you asked, the obvious question is what kinds of new physics would provide potential signals in experiments. And experiments like Bell 2, which is capable of precisely measuring new physics sensitivities in angular observables. And to
Sorry,
answer that, yes.
Sorry, to come back to this point, what values did you find for making this plot? The muon coupling versus electron coupling. How different are
So
they?
electron couplings, new physics couplings are all zero, as you know.
Okay.
And the muon couplings were, of this order, let's say. I will I'll come to them, but yeah, it's not
Like
order one. Yeah,
0.1-ish kind of thing.
0.1-ish, yeah. At most,
And what
because
is the mass scale of the new physics?
no, these are like model independent. So, uh,
Oh,
so these are model independent couplings. So you can decide what your mass and
so
effect.
this is at the B mass scale,
B
the
mass scale.
point mass.
This is at the B mass scale. Yes, the effective theory is at the B scale.
Okay, then I would seriously look at whether mu 2 E gamma is upset or what in this kind of a thing. But anyway, that's just a comment.
Okay, okay. Yeah, and so to correctly estimate detector response, new physics Monte Carlo was needed, and that is what we do. So we developed this new Monte Carlo simulator based on the existing EVT Gen framework, um, and you can find the simulator in this link here or in this paper. So this EVT Gen is a Monte Carlo generator that is used by flavor physicists, experimentalists at Bell 2, because they simulate the decays of heavy flavor particles. But the default framework here is standard model. So if you want to actually correctly simulate detector responses, in presence of new physics, and the theoretical frameworks, including the new physics, was required, and that is what we do. We add a new module to this existing framework, particularly for B to D star L new decays, and that module is publicly available if anybody wants to use it. So the weak effective theory framework is used here. So you'll have all of these effective couplings here. And we consider that the neutrinos are always left-handed. And of course, the standard model case corresponds to the scenario where all of these couplings are zero. Now, different form factors are embedded in the code, but the default choice is BGL. But if you want, you can switch to other form factors if needed. So I will not go into the technical details of using the simulator and all, but what I will show you is an application that we did using this Monte Carlo simulator.
Sorry,
So
this has only the B2C physics, is it?
B2C physics, B2 CL new, but D star, especially D star, because
Okay.
for B2D the matrix elements are different, so all of those physics have to be encoded. So it's particularly B2D star.
And this is all written down at the B scale, and there is no running involved, if I understand.
There is no running involved, so that part you'll have to do separately if you want to,
Okay. All
to
right.
run.
Okay.
Okay, so we study some of the angular asymmetries, and the solid curves actually represent the theoretical expectations for, the black ones are the standard model, and the red, blue, and gray correspond to these three different new physics scenarios that we consider here. And the red bars are the Monte Carlo simulated events, which is done for 50 attobar inverse of data and plotted in bins of zero 0.4 Jeff square. Also, we use some Bell fiducial cuts on the events and plot it. So basically, the red bars correspond to the Monte Carlo data for this new physics scenario 2. We don't show all, I mean, this is just to show that the Monte Carlo behaves well and the meets the theoretical expectations. Okay. So this is just for validation. We did this. But what was more important from this study is that we found that the angular asymmetries are correlated. So let's say you observe a signal in delta AFB. I mean, you go out and measure delta AFB and you observe a signal there. And if that is because of some potential new physics, then you will observe a correlated signal in some other asymmetry as well. So let's say delta is 3 or delta is 5. And if that is not the case, then you'll have to understand that this that signal that you observed is not because of new physics, but for something else. It's something else. And we find that in absence of tensor new physics, the right-handed coupling mainly drives the correlation amongst the observables. So later in 2023, I think when Bell 2 actually started collecting data, they measured some of these angular asymmetries using 189 femtobarn inverse of data and found consistency with standard model. But at the moment, the errors on these measurements are large. And so we need to wait for more statistics to get a clear idea. The tau decay mode is also interesting because, the branching fractions are larger compared to the lighter leptons and compared to, loop-induced absence decays. And increased statistics will allow Bell 2 especially to measure the angular distributions in the tau sector. But the problem with tau is the reconstruction, as too many neutrinos get involved in the final state. So in that case, the angular distributions have to be expressed in terms of visible daughter states from the tau decay. So you don't observe B2D star, tau nu, but then tau subsequently decays. So you need to express them. Let's say if you consider a hadronic tau decay, then you can express it in terms of the pion energy. And that was done by Bhattacharya et al. In 2020. And we took a step forward and calculated the full decay distribution, including the leptonic tau decay. So we have angular observables in terms of, let's say, the muon, the energy of the muon in the final state. So this decay, so the Monte Carlo does not have the tau, the tau decay involved. So one needs to actually incorporate this theoretical framework that we derived in the Monte Carlo to actually, do the application. All right. So as I mentioned,
Lopamudra, you have about 10 minutes.
Okay, yeah, I will finish.
Okay.
Yeah, so as I mentioned, I've worked also on neutral current decays, and most of these have an associated dark sector involved, like inertics, dark matter, light Z primes, sterile neutrinos, light scalars, action like particles, and of course other associated phenomenologies. But okay, because I'm running short on time, I would, of course, not discuss all, but give you a small example. So recently there was this an excess was observed in the B2K new Q squared distribution by Bell 2. So you see here the data point here. There's a small excess in some of the bins here, and the weighted average basically, so I think this was the measurement, but okay, the weighted average considering all past measurements was lies somewhere here. um but it was still significantly deviated with respect to the standard model. And there were many new physics explanations for the excess, but what was found is a two-body decay with the light invisible particle of mass about 2 GeV provides a good fit to the distribution. And so, keeping that in mind, we considered a 2 GeV action-like
Sorry
particle.
to interrupt, just to clarify. So where is that excess? Can you just point out where you're looking at?
So
No,
if
on the
you look
left-hand
at,
side, on the left-hand side.
oh, on the left-hand side, this was the measurement here. This
Uh-huh.
is the standard model, this line. This
Okay.
was this is the integrated branching fraction.
Okay.
But if you look at the distribution, this was what was observed, basically.
Okay. Thanks.
Mm.
Sorry, like the form factor in this, how is that obtained?
For B2K form
Yeah, yeah.
factors are already known from lattice and other measurements. So
Okay.
that
Uh,
that was,
which
yeah.
is the one that is, used in this kind of, like to say that there is an excess of this sigma. So is it from the lattice or from experiments or?
I think lattice, because at present lattice provides the most precise, you know, measurements on the form factors. And for B2K, I think only one form factor, which is like, so you need basically two form factors at most. And I think for B2K, only one form factor, which was, I think, F plus, that was required. And F plus is given by the lattice collaboration. Yeah, I think that was used.
Okay.
Hmm.
And if you look at B to KL new and extract the form factor from there, how do they compare? Do you know?
You won't have B2K L nu because this is a neutral current transition.
No,
You
no,
will
to
have
extract the
B2K
form
LL.
factor. Yeah.
To extract form factors, I mean, extraction of form factors is like a different kind of technique or analysis that
No,
is
no,
used. I
but
mean,
to
by
zeroth order, I can look at B to KL new. That's a related mode, right? The form
not L
factor
nu,
should be
LL, L plus L
okay.
minus.
That
Yeah.
too, yeah,
So they'll have the same because the form factors is a representation of the hadronic part. It does not, it
that's
has
right.
nothing to do with the leptonic part.
Yeah, that's precisely
So,
what I'm saying. So because it is you can get a form factor from those. The question
mhm.
is, how do they compare with the lattice? I mean, do you, are they comparable? Are they very different?
No, I think it's the other way around. I mean, the form factor that is used by when the experimentalists, do this analysis is what is given by the lattice group. So the form factors, I mean, the lattice people, they actually do the analysis, B to K or K star transitions. I mean, that kind of an analysis to extract, form factors.
No, no, no,
And
that is fine, but I'm just asking, one
mhm.
could take the form factor from experiment, and if you
Yes.
just compare the, like the errors that you get extracted from experiment versus what the lattice gives you? How do they compare, and which one, whether they're all consistent, whether there's a
I
difference? It's
think
just that kind of a
for
question.
B2K, the F plus is quite well known. I mean, they are comparable. So here, because you see an excess, of course, you cannot, I mean, you cannot model this excess with the form factor. I mean, if
Okay.
that's what you're trying to indicate.
No, the excess is there because whatever you have already plotted, all the other colors, the form
Yes,
factor has already gone in, right?
gone in there. Exactly. I mean,
Yeah, so
I
if
mean,
that form factor is wrong, then all these numbers are wrong, right?
are
Yeah,
wrong.
that's kind of the thing, right? I mean,
Yeah.
we have
That
putting
will not work
our
out.
faith on some extraction of the form factor. And that was
Yes.
just a question on how robust is all of this. If you use different ways of doing the same thing, are they all kind of consistent? Will they be in disagreement? So that is like a zeroth order question
Actually,
before you say that it is a two-body
I can
decay.
frame this a little bit differently. Suppose you take B goes to KLL
Yes.
and take B goes to K nu nu
Yes.
and
And
plot this right-hand side graph for both of them.
right, you will still,
Using any one set
observe
of form factors. And
yes.
will you see an excess in KLL like you see in K nu nu is the question.
No, you will not. Yeah, so
Then of course it means that if you've used the
because
same
it
form factor
was,
for
yeah,
both,
order
then
of
of course there is
magnitude,
a discrepancy, right?
difference in
And
this.
then it cannot be due to form factor. It should be due to
It
something.
is not due to form factors. Yeah, that is what I'm trying to say.
Okay, fine.
Okay, yeah, you should continue.
So, yeah, so we consider this 2 GeV action-like particle in order to explain this excess. And model independently, you can have this kind of flavor violating couplings to the standard model. And we consider coupling to B and S quark. So we have couplings like CSP A and CSP V, as you can see here from the Lagrangian. So you'll have contributions to both B2K A and B2K star A, where the ALP is basically invisible. Now, the B2KA is measured, but the K star A, you only have an upper limit. So if you have to respect that upper limit, a part of the parameter space is ruled out. But you still have a region of the parameter space where you can explain the excess with the 2 GeV ALP. And we find that the decays, the U1 breaking scale FA is about 10 to the 8 GeV, and for 10 to the 8 GeV, the decay length is about 65 meters. So basically, the ALF decays outside the Bell 2 detector, which is why you observe this kind of a signal. But then the question was whether this 2 GeV ALP can be a potential dark matter candidate. And we find that it cannot, because it firstly, it couples to the standard model. And so you'll have the ALP decaying to other standard model particles. So you'll not be able to produce enough dark matter. So we consider a simple extension where this ALP basically acts as a portal to the dark matter. So you have this fermionic dark matter chi. And there is a two-step freezing happening. So first, the ALP is produced from the standard model bath through the decay and scattering processes. And so you slowly build up the action-like particle yield as shown here in this sine curve, YA. So the ALP quickly reaches thermal equilibrium, but then subsequently decays to dark matter particles whose yield is then frozen in. Okay, so you'll have the freezing in of the dark matter. And when we plot, this is the constraint plot in the CQ, which is the coupling of the ALP to the quarks. And we actually consider universal quark couplings. So, let's say C SB and CBB couplings are all equal, but this does not actually affect the other phenomenologies. So we've checked that. So the CQ, and if you plot it in the CQ and C chi plane, this is the allowed parameter space where you can simultaneously explain the dark matter relic as well as the belt to data, and the gray shaded region are excluded. Okay, so you can have
Sorry,
dark matter. Yes.
sorry, quick question. So the standard model directly cannot couple to dark matter, is it? By just integrating out that axion, you will
Hmm.
generate an effective interaction.
Yes.
Won't that thermalize this dark matter, and won't you directly have a way of producing the dark matter through that effective coupling?
If we integrate out the dark matter.
Integrate out the A, like you integrate out your A and P.
Integrate out the A.
Yeah.
I mean, at the B scale, B meson scale,
No,
how
this is
things
not the
like
question about the B physics, but about dark matter. So then why do you need then this freeze-in scenario and all that? You will, if it is thermalized, you directly have a production of dark matter, right? It is a thermal dark matter then.
I think in that case, thermal dark matter is that. I don't know whether that's possible. Let me think. I mean, you're saying B2K chi, something like that, right?
Yeah, yeah.
I think then you mess up with the distribution here. So if you want to
No.
actually
This is not a statement about the flavor physics, but about dark matter. No, it's a question
okay,
about
I mean,
why do you say it is freeze-in, right? Your plot is saying that first you will produce a population of A,
A
and
and then
A then decays to chi.
yeah,
That's this
because if
statement, right?
you don't have this here, so our idea was to simultaneously explain both. I mean, independently, if you want to,
No, that's
like,
okay. But the
yeah,
question, like, then you don't have a freeze-in scenario. If you have an effective vortex which is sizable, then you have
then
a thermal
you can
population
like
of dark matter.
thermal population, which then you freeze out. That's what you're
Yeah,
trying to
yeah,
say, right?
that's right. That's
But
right.
with freeze out dark matter, I mean the order of the couplings that you have, uh, you will not be able to explain the excess. And our idea was to actually have a dark matter model that
No, I
also
mean it is
explains
a question on the parameter space. You have
independently.
you have assumed some parameter space, right?
I've assumed some parameter space. So
So for that parameter space, if you integrate out A, what is the size of the effective operator, and is
oh
that
no,
sufficient
so
to
you see
thermalize?
the coupling is like order, 10 to the minus 9. I mean, coupling over FA. And with that, you will not be able to like freeze out dark matter.
Okay, all right.
Yeah.
Yeah, okay. Yeah, okay. So yeah, you should just maybe finish in the next few minutes.
Yeah. So I think that was my last
Okay,
slide.
all right.
So what I wanted to show is that it's possible to simultaneously explain the efficiency decay with a dark matter model and also the dark matter rally. So I have some future research plans. I'll just go through them quickly. First, I like to, study the phenomenology of flavor violating action like particles. I already, gave you an example how they can affect flavor physics. So the idea is, if one can investigate whether it's possible to address the flavor puzzle of the standard model and the dark matter problem simultaneously um, through the freeze-in mechanism, which is not actually something that people consider when they consider an ALP dark matter. So firstly, the case I showed, the ALP was a mediator. So it's like the portal. So whenever you have ALP as a dark matter, the misalignment mechanism is usually what people do, but yeah, we'd like to see whether you can produce it through freezing. And then, of course, put bounds on the flavor violating couplings from upcoming measurements. We already attempted to test the reach of, future muon colliders in probing the LFE Alps. So there is this proposed mu Tristan collider, which is the mu plus and mu plus E minus collider, proposed by some Japanese people. And we found that uh, that collider will be able to actually exclude large parts of or probe the flavor violating mu tau alp coupling to a great extent for GV scale alps, which we are interested in. So lighter alps are already quite nicely constrained, the parameter space of very light alps. Next, I want to study non-standard neutrino effects in B-decays. So I already showed you, we studied the B2 D star L nu or tau nu decays, but the neutrino was always considered to be left-handed. But then you can have, contributions coming from other non-standard neutrinos, which may affect the decay distribution. So you need to incorporate all that, construct the decay distribution, and see if there are, interplays with the FCNC sector. So B2K or K star nu nu. As I showed you already, this 2GV two-body decay can actually produce the or fit the data quite well. It was also found that a three-body a light, about 0.6 GV neutral particle can also, fit the excess quite well. So if this contribution is from a non-standard neutrino of about 0.6 GV, one can study what effects it can have in the charge current sector and so on. And of course, incorporate these in Monte Carlos to assess the new physics sensitivities. So far, I've mostly studied semileptonic and leptonic B-decays, but I would also like to step my foot in non-leptonic B-decays from new physics perspectives. For example, there's a puzzle, known puzzle in the B2 pi k decay, and because it also is like a B2S kind of transition, it was found that combined explanations of these anomalies is possible within the SMEF framework, but there are no UV complete models that can accommodate these puzzles simultaneously. One may actually come up with new sources of CP violation that may have, implications for the observed matter asymmetry of the universe. So that's all. Thank you.
Okay, thank you very much. Any questions? Okay, I don't think there are anybody on Zoom, any questions? Okay, we had plenty during the talk, so I think we'll stop here, Lopamudra.
Okay, thank you.
Yeah, thanks a lot.
Thank you.
Bye-bye.